Hey there, folks. How you doing? Today we are going to talk about streams, and we've been talking about streams on and off all semester. And by now, you know that when we say stream, we don't necessarily mean anything in particular. For geologists, for earth scientists, a stream is just a sort of catch-all word for any body of water that's running through a channel, a ditch. All right, and the reason is if we start to talk about rivers or streams or creeks or cricks or brooks or whatever, you get my point. We start talking about, or thinking about, I should say, different sizes. And that's not really important. This picture itself, when I first put it on, it's really hard to get scale. Right? It could be just, somebody's taking a picture downstream. Used to be little rocks or pebbles. It's not until you notice those guys down there on that one flat rock. Yeah, exactly. Now the scale changes right away. Yeah, I purposely picked this picture. It's kind of cool that way. It's not until you see those guys that you get a totally different perspective. Those are really, really, really big rocks all of a sudden. Oh, it seems fun though, too. I wouldn't do it nowadays, but in my youth. Well, it's the last lecture. So, streams. Any channelized body of water, regardless of flow, it must flow. So, you want to use like a canal. Even a canal flows a little bit, but and we get rid of canals by saying can't be man-made. The first slide, I didn't really talk about it too much, but the opening slide said streams, surface water drainage systems, and that's not a really glorious way to talk about them for all that streams are and can be. And we tend to love streams as humans. We visit them, we live near them, we develop cities and nations near them. And in the olden days, there was good reason. Transportation was a big one. But in the end, they are just ditches with water flowing through them. The land drains itself. The land drains water into low spots. And over time, because, as you know, streams can carve into the earth, they establish these channels. But if you back up far enough, if you get that bird's eye view, so to speak, you realize that it is fairly organized. There are major high points. There are major low points. And we start talking about not just watersheds, which is a word you might know, but we start talking about drainage basins, okay? And then when we talk about basins, then you have divides. You may have heard of the Continental Divide. It's essentially the Rocky Mountains, all right? So it's not a complex thought here. This is the same idea as if you were standing outside while it was raining on your sidewalk and you look at your house. And all the water that flows, that lands just to the left side of the peak on your roof is going to flow down that left side. And all the water that lands just to the right of that peak is going to flow down the right side. Why? Because it's what it does. It's gravity. It's a slope. It's, all these things. Well, all that's all that's going on out here in the world. Okay, as the water rolls downhill, and we tend to see these, like I said, these patterns. And it doesn't even have to be one stream. One stream could feed another stream, and could feed another stream, and we're going to see we have vocabulary for that in a couple minutes. but you get this whole network of streams. So these are some major divides or basins for the continental, well, not even continental U.S., for North America, really. Lovely shades of brown they use for the most part here. You see most of the Midwest there is essentially penned in by the Rockies to the west and the Appalachians to the east. And those would be our divides. They don't mark the one on the east, but you see Continental Divide is pointing to that black line on the west there. We don't have a mountain chain to the north around the Great Lakes there, but it does dip down enough that, you know, the water that falls just along that black line drains into the Great Lakes, and the water south of it drains, well, to the Mississippi and a handful of other large streams there. Everything over here more or less drains out Chesapeake Way. Okay, that's a great big area over here. You guys, of course, know you got the St. Lawrence up there, big waterway, no doubt. But for the most part, we talk about draining out to the Chesapeake area. North of us, things drain towards the Hudson, okay, and so on and so forth. I'm not going to have you label a map or anything like that. Don't worry about that. Just trying to give you an idea of how things move. This can be, I don't want to say small scale necessarily, but this could be stuff, you know, you're going to see watershed signs if you pay attention to such things. If you're traveling east towards, I don't know if it happens before Syracuse or before Rochester. I think it's before Syracuse. You'll see a watershed changing sign. If you're traveling toward, that was west. I don't know if I just said east, I apologize. West. If you're traveling to the east, just past Albany is actually the highest point on 90, like all the way to North Dakota. Something it's mind-boggling, really, because it doesn't seem that high. But that is a huge divide. And again, just after that, you're going to see a watershed sign. All the water to the east of here drains to the Chesapeake area. Everything to the west of here drains. Kind of the Mohawk is a big one around here. Even the Mohawk, you know, has to flow to something or somebody. So the signs are there if you're looking. Well, one of the things that sometimes comes up is during the TopoMaps lab. You guys are looking, especially if you live in town or around here, and you're looking at Utica East or Utica West, and you found your neighborhood, and you're like, hey, why isn't that creek at the bottom of my street? It's not on the map. It must be new. No, it's probably not new. It's just a function of scale. All right, and that bottom layer here, you know, that might represent the topographic map and the streams that are on there. But if you were to zoom in on just one simple little fork, which is what this top picture is showing us, you see that it's indeed fed by many, 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 many more. This is exaggerated, I'm sure, but many, many, many more little channels. Those are called tributaries because they contribute to the mainstream system. So we have all these tributaries that feed into the mainstream, excuse me, and that mainstream we call the trunk. Okay, again, around here the Mohawk is a great example of that. There's a lot of feeders that go into the Mohawk. Again, some of them make the map cut, some of them don't. All right, this didn't exactly benefit from being enlarged, a little fuzzy. So I used to draw this on the board, but now that we're in the digital age, it's time, and then the folks online can never see what I was drawing. So a semester or two back, we got an image from the USGS there, that's the U.S. Geological Survey, for some teacher, I suppose, to have just this very same conversation. We're interested in learning some vocabulary for a cross-section, which we're looking at, of a stream channel. All right? And I suppose stream channel ought to be our first vocabulary word. The channel is that ditch that the water's flowing through, okay? An elongated hole, whatever you want to call it. But the channel itself, okay? Now, making up the channel, we've got a stream bed and some stream banks. The bed, you probably knew this already, is the bottom, okay? The stream banks are the sides of the stream. Now, a lot of you may have said, or your uncles or grandpas or whoever you go fishing with may have said, oh, we're standing on the stream banks. Not if your feet weren't wet, all right? We've got a word for up on the side, up on the top. I'll give that to you in a minute. But the banks are the sides of the stream. So if you're in there and you're wet, yeah, maybe you are standing on the banks. But more than likely, you're up on the floodplain, all right? And the floodplain is that wide, flat area. Sometimes it's on both sides of the stream, sometimes it's not. In this picture, they drew it on both. It really depends on, your valley that you're in. Floodplains are plains for a very good reason. A plain is a large, flat, broad, flat area. Streams, and we didn't get into this so much in this class, environmental science, as we do in my geology class, but streams carry a lot of sediment, okay? And they also move or transport a lot of sediment. They wear away, they weather is the word. I guess I just used the word. They weather away a lot of sediment, and that's how they can transport it. When they flood, when they go up over their banks, they slow down a lot. And that slowing down means that they can't carry as much sediment as they were just a few moments back when they were trucking along through that stream channel. There's some math that explains it. All right, we'll talk about it a little later. So what happens is all that sediment comes up and woof, it falls out of suspension. And what it does over time is it fills in, levels out all those little nooks and crannies that were there alongside the stream the whole time. And again, as I said, over time it makes this broad, flat area. So much so that even though once we stopped using streams for boats and transportation of goods that way, and we started moving on to trains, well, we built our train tracks right there. It was so nice and easy. You had a path more or less there for you already. Yes, hence the word floodplain. It did flood periodically, but that was apparently worth the effort for them because, it was a nice area to build on. Now, between the banks and the plains, we've got this other word here, levee. All right, why they spelled it with one E on the left and another E on the right, I have no idea. We generally spell levee with two E's. Yes, levee. Oh, the one on the left, yeah. So, a levee, you guys have probably heard the word. There's a couple songs about levees, and we all know what happens when the levee breaks and so on and so forth. But levees are, again, deposits, just like the floodplains are. And if you think about a stream having a system energy, okay, and that energy is dependent on its velocity, how fast it's moving. As soon as it comes up and over those banks, that velocity drops like crazy because it's no longer confined. And we'll actually have, as I said, an equation a little later to show you kind of what I'm talking about here. But that velocity drops like that. And because of that, the hardest stuff for it to carry, it drops first. So the biggest sediment sizes. Again, in geology, we talk about boulder, cobble, pebble, sand, silt, clay. Okay, and silts and clays, obviously, the smallest. Boulders and cobbles, the biggest. More than likely, this stream wasn't moving boulders and cobbles, even if it was about to flood. But all that stuff in the middle, from mud to sand to what you would call gravel, that was flowing along. And it comes up and over the banks, and whoosh, the bottom drops out of that velocity, and all that big heavy stuff falls out. Well, it builds up those levees a lot faster than it does anywhere else. Right. You okay?
Yeah.
So we see these levees, they form ridges along the stream channels here. And again, they're just flood deposits, just like the plains. But it's the larger sediments, so they build up a little faster. And what we find out is that they actually sort of end up being natural flood deterrents, if you would, because they're building up the banks of the stream even more. But eventually, it'll happen again, and the water will come up and over the levee, and it might add a little bit to the levee. It might wear the levee down a little bit, and it'll add more stuff to the plains. But I certainly don't want you to worry about this other vocabulary word on here, but it's worth talking about because it reminds us what streams can do. This abandoned floodplain or terrace over here on the left side. If you're like me, you may have been walking along and look at a scraggly little stream, and then look at the valley that you're in, and say, how in God's name did this silly little thing carve this hole? And the obvious answer, and I'm sure you arrived at as well, it must have been bigger at some point. And it probably was. But when we see these old floodplain levels here, it reminds us not only that the stream used to be bigger, but that it really, really was carving down through the earth. And at different points in its life, and it represents, a good chunk of time. So just a quick review. If you missed any of those terms a couple minutes ago, those are the ones we want you to know. The channel itself, which is made up of the bed and the banks. The levees, which are just outside of the stream banks, and then the floodplain on the other side of the levees. Here's a much dramatized version of what we've been talking about. That's one hell of a flood there in the middle picture. But nonetheless, they want to prove their point here, illustrate their point, I should say. So we have our stream on a normal day there in the first picture, and your floodplains on either side, and then we've got, as I said, the Great Deluge. And we see the tan sand deposits there. Then when the water recedes, if you compare picture A to picture C, you can see how then we have built up those banks quite substantially and making levees. Now, once you know about these things, you might start to notice them, start to pay attention to them, dare I say. You're going to see some that seem exceptionally huge. And a lot of times the cities or the towns take it upon themselves, because they've got a lot at stake here, especially if they're very close to a river, that we enhance these. Sometimes it's so ugly, as in they'll just pour cement over them. Sometimes they do it nicely, and they'll put grass and whatnot on it too. It really depends. And as I said, as you drive around and look out the window, you will see things like this. One of the most extreme cases, and this was well before there were cell phone cameras, was a town or two over from where we used to live years ago. And just as we were we never went to the town itself. We were always going past it to somewhere else. But if you looked out as you were going over the bridge to the passenger side, if I recall, it was their downtown area. Just picture an old-fashioned kind of downtown. And as I said, they're right on the stream. Well, they had built up behind the entire strip. Thing must have been damn near 1 story high, for their buildings. And again, that stream must have had a pretty bad past, or at least occasionally went crazy, enough so that they invested. It was an old small town, but they invested what money they had. Maybe they got grants, who knows, to enhance the hell out of that levee. Because again, it wasn't even that big of a channel. So I just, but it must have went. Like I said, things must have happened uphill from it. A lot of paving will do that. That's what they were blaming all of Sequoia Creek's flooding over the last couple decades is development further north. The more blacktop you put down, we did groundwater in here, right? The more blacktop you put down, the less infiltration you get, the less percolating into the ground, so the more water stays at the surface. Anyhow, lest I digress. But so not all levees are natural, is what I wanted to get to. All right, now we've got some more stream anatomy, but from a slightly different angle. We're not looking at a cross section so much, but as a top view. And we want to take you back to talking about the drainage basins. And we're in a basin as a whole, and where that stream is starting, we call the headwaters. And as you see, the headwaters don't have to be one particular stream. It could be any number of tributaries. Remember, tributaries contribute. So we're catching all the water that falls in this particular area. That's called the headwaters. All right, and we're funneling it downhill, and we're feeding one main stream system. They've drawn this rather nicely that if you start on the left and move to the right, you see how that left stream slowly gets joined by another one and then another one, and it just makes your main trunk stream there. The trunk stream is what we call the main stream. Now, it doesn't happen a whole lot, but it does happen, and I want to point it out. Just as we have tributaries, there's something else called a distributary, and it's the opposite. Mainly, it's a function of topography. It's a function of the lay of the land. And every so often, a stream will branch off, and instead of contributing water to the mainstream system, it pulls water away from it. It distributes, so distributary, okay? So we have two words that really, use that tributary there. Tributaries which contribute, and again, distributaries which remove water from the mainstream system. We don't have one on the picture here. As I said, I just wanted to acknowledge it. So anyhow, we've coming down from the mountains here, from the hills, and we've got our main stream now. We're done contributing to it, and we see that weird little braided looking thing, which for some reason they did not drop a vocabulary word for. I'll tell you what it's called, but I won't hold you responsible for it. It's actually called a braided stream, and we do see these happen a lot. Usually there's a whole lot of rocks and gravel in the way, and they tend to break the stream up into a bunch of little streamlets, if you would. Not a real word, but and then at some point they come back together and reform that stream trunk there. Anyhow, so the stream's flowing along, and all of a sudden we start to see all these bends and curves. And of course up top in the headwaters, sure, it goes around a curve here or there, but not like it's doing down in the second half of this picture. And we call those bends or turns, we call them meanders, okay? And we're going to talk a good bit about meanders in a little bit here. They increase with age, so if you see a stream that is very meandered, all right, that means it's probably been around a while. On the other side of the meanders, I'm not going to talk too much more about it. As I said, they do have their own slides, so we'll come back to meanders in a bit. Floodplain, we already talked about floodplains, okay? And that's to either side of your stream there. We got something new down here at the bottom, though, delta, okay? You guys have heard of deltas, whether it's the Nile Delta or the Mississippi Delta. There's a handful of deltas out there that that make it into common conversation. Delta's a name for the D, the triangle letter delta there, and they are shaped that way. That's why we call it that. Now, right now, you see that it's broken. It kind of maybe even looks like that braided stream a little bit. See all those tiny little streamlets there. Well, we want to take that all away except for one for a moment, because this thing was built over thousands of years. So remember what we talked about with streams, how they transport sediment, and how that sediment transport is dependent on velocity. So we're coming down this mountain here, the hillside, whatever it happens to be, and we're going down slope. It's trucking along really nice. Okay, looks like we got a bit of a cliff here, so it's really picking up speed there. And then boom, we hit these floodplains. We hit this flatland. That takes a lot of the oomph out of the stream. Well, when it hits that body of water down at the end there, even if there's waves there, that doesn't really count as movement. It's like that stream hit a brick wall, all right? And it drops almost all of its sediment immediately. So what that does is it builds up a bit of a deposit right there. Stream continues to come on down. Stream continues to deposit sediment, and at some point it just sort of chokes itself off. It doesn't become, it's not big enough for that stream to flow through it anymore. So what happens is it backs itself up, it floods, if you would, and it finds the next little low spot and starts to cut a channel there. And so that's the next little streamlet. And that goes on for 100 years, couple hundred years. Does the same thing. Eventually it chokes itself off, it backs up, finds another one, and over time you get this fan-shaped, this delta-shaped deposit. I always use the example, as silly as it may seem, as one of those broadcast sprinklers that you might have in your backyard. You know, the ones that go, and then they all go back at once. You know, comes all the way back and starts over again. Well, it's a very, very, very slow version of what that sprinkler's doing, okay? And over time, from left to right, it could be right to left, it doesn't matter. It's neither here nor there. It could have come down the middle and then built off to either side. That's not the point. But that this land has built up over all these years. Now, go back a moment to the conversation we had when we talked about groundwater and how we talked about Louisiana that is wearing away down at the bottom. Okay, we said that the ocean, and the same thing is true here. The ocean is constantly beating at this delta, but we have to presume that since it exists, it's bringing more sediment than the ocean can wash away. Well, what we said with Louisiana down New Orleans is that because we've cut off the flow of sediment, because we use the Mississippi so much, remember that conversation? And we're not allowing that delta to continue growing. So instead of keeping some sort of equilibrium of sediment versus waves, well, it's simply just being washed away by the waves. So here's that process now. We've come full circle, and we're showing you how the delta is actually built, and subsequently how we messed it up with the Mississippi there. All right, last but not least, we have the term mouth. Mouth is where the stream lets out, okay? It's where it ends. Haven't gone horribly far. We went from the head waters to the mouth. You know, they could have went for foot or tail, perhaps. I don't know. But I get where they're coming from. Mouth, it's pouring out, it's flowing out. But yeah, so the stream mouth is where it ends. The stream headwaters are where it begins. And again, here's our list of vocabulary that we want to make sure you understand, or at least recall all those terms. All right, so I told you we'd talk about meandering. So meanders are curves in a stream, or bends, B-E-N-D-S, if you can't understand the word I'm saying there, bends in a stream. And they're caused by differential weathering and erosion and deposition. That sounds like a bunch of sciencey gobbledygook there, but it's actually fairly simple. You want to picture a stream going around a curve, going around a bend, okay? And when we're doing that, we talk about two things. We talk about the outside of the turn and the inside of the turn. To use my elbows up in the air here, to use my elbow for an example, the bony part of my elbow is the outside, okay, of the turn. My elbow pit is the inside of that turn. And then we want to remember some of the wonderful things we talked about with water, all right, and how much water loves to stick together. So what we really need to picture now as we're looking at a stream is that it's really bands of water molecules going by, moment by moment by moment. It's nothing but these water molecules chained together, okay? And so what we're saying then is that the outside of the curve weathers and the inside deposits. Well, how are we going to do that? Well, here's what's going on. Anybody marching band when you were in high school? Marching band. Okay. Usually I jump to then talking about car racing or horse racing, but someone reminded me last class actually about track, and we usually get a couple people that ran track at least. And even if you didn't do any of that stuff, you're probably aware of this, we dare say even call it a philosophy, but if you are on a race and you're going around a track, do you want to be on the inside track or the outside track? It doesn't matter. Well, it does. It does. If you're running, it doesn't matter because something I learned just a little bit ago. But let's say you're a race car or a horse. You want to be on the inside. Is he right, you guys? Why do you want to be on the inside? It's shorter, all right? It's a smaller circle than the outside. So if it's just a simple race, who's going to get around first with the least amount of effort is the guy on the inside track. Well, what I just learned about running track, that's why they stagger the starts. You guys probably all knew that, and that's why you said it doesn't matter. I didn't know. I mean, I should know that. It makes perfect sense. But I never realized that's why they staggered the starts. Anyhow. So the outside track is longer. So if you're racing, okay, you got to work twice as hard if you're on that outside track as whoever's on the inside track. Marching band, we would use the analogy how the folks way out on the end have to march faster than the people down in if you're making a turn, because you all got to keep in line, right? So, at any rate, the same thing is true here. The stream doesn't think about it, it just does it. It's physics. So on the outer end of that curve, the water's moving faster. On the inner point of that curve, the pivot of that curve, if you would, the water actually slows down a little bit. Add to that what we just told you about with the faster the water moves, the more powerful it is, the more stuff it can destroy or carry. The slower it is, we start to see stuff getting dropped and deposited. So what we see then is on the outside of the turn, the stream actually gets sort of eaten away, worn away. And on the inside of that turn, we get deposits. Now, this doesn't make the stream wider, but what it does is it moves it. All right, I'm going to show you a picture right now. All right. So we look from one square to the next square, you see those meanders in the middle are moving closer together. They're not getting wider. They could. Arguably, you could come up with some math to show that they could get wider. But right now, we simply want to move those together. And what this shows us is that as this stream ages, it was the last bullet on there I mentioned earlier, but not just now, okay? Meandering increases with a stream's age. So we're taking these natural variances and we're accentuating them with the erosive and the weathering power of water. And we're offsetting that then with the deposition on the inside. So again, if you've ever walked along a stream, spent any time at the stream, you're going to see these little gravel bars or sandbanks and so on and so forth. Okay, those should be on the inside of a bend. Check next time you're wandering around.
That water just be stuck there.
Huh?
Between the sandbar and the...
Well, we're going to get there. We're going to get there. This slide isn't even really about meanders. It's about what meandering can do. So you see oxbow formation, or sometimes they're called oxbow lakes. Okay. So what happens is we move from the second square there, where the meanders come closer and closer together. We can get to a point where the meanders actually get cut off, and it channelizes through. And again, not that the water is thinking any water doesn't think, right? But we talk about it that way. It helps us explain things. Water, like everything else on the planet, follows the path of least resistance, right? So it could go all the way around that meander and then around that bend and then around the other bend and then back, or it could just flow straight through. It's going to flow straight through. And what that does, again, over time, is it entrenches that in, it cuts into there, and eventually that meander can get completely cut off, okay? It's not that their sand was put there necessarily, but that it dried up right there, all right? And you're going to see a real picture in a moment. And so what we just formed is what this oxbow is, and science has a lot of antiquated terms. Geology is one in particular, again, because so much of it comes from those early observationalist folks that I like to talk about. So an oxbow is an old, because there's a newer word for oxbow that we still don't use anymore, which is called a yoke, all right? But remember, you've seen these in movies, like Middle Ages movies, where they're using an ox to plow their field, or they're pulling a cart through town. There's that big old wooden horseshoe-looking thing over their shoulders. That's an oxbow, all right? Which, again, if you know anything about it, you probably call it a yoke. We don't even use that word necessarily. I suppose somebody's still out there farming with animals, but you put that yoke is there to hold, like I said, a cart or a plow or whatever. So this resembled that to these folks, kind of like you look up the constellations and you see that's a hunter, really? Okay. This is a little more, at least it looks like it. But and again, these things aren't necessarily even visible when you're walking along. You need to get up on a hill, or even better, fly over in an airplane or a helicopter, and then you start to see what's really going on. Because if you were out there wandering through the fields, hunting or whatever, just playing as kids, you're going to see something that's long and narrow. It obviously equals a stream in your brain, but it's probably not flowing. You're like, okay, this is weird. And if you walk long enough in one direction, it's just going to disappear. And you walk long enough in the other direction, it just disappears. It's a cut-off meander. All right. Sometimes they swamp in on the back ends of it. It really just depends how much rain you get in that area. But as you look at this stream, as I'm hoping you're doing while I'm just chittering to you, you see, you could probably guess which meander is going to go next. Okay, which one's going to get cut off, and then which one's going to get cut off. And the funny thing about this is, we told you, that a young stream is straight and narrow, and then as it get old age, it meanders again. But then if you cut off those meanders, you're heading back towards a, well, I wouldn't call this straight, but certainly a straighter stream. You kind of almost come full circle then. So meandering increases with age, okay, and oxbow lakes are cut off meanders. Questions about why meanders form? Again, they're just natural bends that are accentuated over time.
It's really interesting because it makes it hard to tell where they got cut off exactly. Right.
That one in particular, yeah, that's a sticky one, and
I think I figured out how it got cut off.
Yeah, it's a big gap. Right? Where do you think it came in?
You see a little before the one where, okay, where it splits into like two, and
Oh, okay.
I think it.
Oh, you think it was all the way over there?
But
Oh,
then
big.
it wasn't. So I think that's how it got separated.
That's a good. I mean, you know, I'm so used to showing this picture. This picture. You know, the oxbow doesn't have to be that close. I was, you know, I certainly, you could certainly be right. Let me put it that way, because that is it's a lot of green, as they say. But yeah, it certainly could have come from over there. But that one really is isolated.
Yeah. And in the top left, you can see another one about.
Well, and I would say that would just go straight across almost, and you'd end up with a little divot in it. But yeah, it'll be interesting to see what that looks like in a couple hundred years. All right, changing gears entirely, and now we want to talk about flow rates in a stream. So again, if you've paid any attention and walked along any streams in your life, which hopefully you have, and if you haven't, now you've got some homework for over summer here. You know that you know, streams flow at different rates. Some streams are really slow, some streams are really fast, and even at that, you could be at one point in the stream where it's flowing, let's just say really, really slow. You go downstream a little ways, and all of a sudden it's flowing super fast, or vice versa. All right. And the next time you encounter that, I want you to stop, and I want you to look at where you are now, and then I want you to look back upstream, and you should be able to notice something like the channel gets bigger or narrower. That's the easiest way to change the velocity. So my point is that there's 0 point in remembering, oh, the fastest stream on the planet flows at this rate. The typical stream, you know, flows at that rate. That's silly. And there may not even be numbers like that. But what's much more useful is trying to give you some information of, you know, what reflects what you actually see, what reflects what you see in the real world. So we're going to focus on that. As it turns out, there's actually 3 factors that can affect that. Now, the first one you learn very, very, very early in life: gradient. And it's not that as a child you know the word gradient or even slope, but you learn very, very quickly that if you put your toy car on a slope, it's going to zoom down it and go across the floor. Or if you are at the top of a hill and you're outside playing and you roll down that hill, my goodness, you're going to go fast. We figure out slopes really quick. And then you got to climb up it, which, you know, is going to take some energy too. So the first one here is pretty simple. And each of these gets a slide, so I won't go into it too much just yet. The shape of the channel, you might not have thought of that one. We just sort of foreshadowed a little bit. Okay. And then lastly, discharge. Discharge is a horrible word here because, you know, when we think of discharge, it's not usually a good thing. But all they mean when they say discharge is the amount of water that's flowing through something, the quantity of water. And in fact, we're going to use Q as a variable here in a couple minutes for quantity, but discharge is the term they use. So the amount of water that's in the stream. So 3 factors, okay? The slope of the stream channel, the shape of the stream channel, and how much water is in the stream channel. All 3 of those things can affect that flow rate. So, gradient first, as I said. Excuse me. Gradient is very similar to slope. For some reason, when we're going up something, we call it a slope. When we're going down something, we call it a gradient. I don't know why. Same formulas and everything like that. Don't worry, we're not going to be calculating slope. But anywho, you already know. Okay, the steeper the slope, the faster something's going to go down it. Gravity, whatnot. All right? Not going to belabor that. This one, though, as I said, might take a little bit of thinking. First, we're going to talk just about the first 2, A versus B. All right, and we've got a narrow and deep stream versus a shallow and wide stream. And this is the one, as I said, as you're walking along in a park or wherever, you are quite likely very easily to notice. Again, as I said, if you're walking along a stream and you notice a velocity change and there isn't an obvious hill, all right, I want you to stop and look back to where you just came from if you can see it from there. And more than likely, if the stream just slowed down, you're at a wide spot, and upstream it was a lot narrower. Or vice versa. If the stream just got really, really fast, look back and see if it isn't a good bit wider where you just were. So all we're telling you is that a narrow and deep stream flows faster than a shallow and wide stream. And it's all about surface area. I used to try and explain this and convince you guys that it was the same amount of surface area here, but I think a much better way to do that is to say that it's the same amount of water in both situations. And we have the same amount of water in the top in A as we do in B. In B, it's just spread out over a lot more rock. And that spreading out gives you a lot more friction. And as you know, friction slows you down. So that's why narrow and deep is faster than wide and shallow. All right, again, given the same amount of water. We're sort of building up to that. Mother Nature doesn't have to do math. Our math is an attempt to explain what she's doing. But we're simple. I'm simple, at any rate. Maybe some of you are in Calc 3. I don't know. Okay? And if so, you could do differential equations and all that awesome stuff, which is what she's apparently doing. We're going to keep as many variables constant as humanly possible when we talk about this stuff. And we're only going to change one variable at a time because that makes things very simple. But again, it's not happening in nature. All right, so now we want to talk about A versus C. So same size channel, essentially, but in one of them, we're going to put a whole bunch of rocks in it. All right, and we're going to tell you that with regard to the rocks, smooth versus rocky, what we're looking at is more surface area, okay? Which again, surface area equals friction, which should slow it down. Now, if you happen to have a hobby of going kayaking or canoeing or paddleboarding, you might have a little flag going off in your head or a little question at any rate. You're like, wait a minute. I've been in streams, and when the streams get rocky, quite often we've got some rapids going on and stuff like that, and that is definitely faster than before. That doesn't make sense, and you're right. We will, if we have time, we'll touch back on that at the very end, because we need a few more things thrown in to help us explain that. But just as a general statement, again, keeping all other things even right now, smooth versus rocky, a smooth stream is going to flow faster than a rocky stream because of friction. So narrow and deep versus wide and shallow, narrow and deep wins. Smooth versus rocky, smooth wins. So there's a second feature there, and that also talks about our channel shape. Lastly, discharge. All right. Discharge, as I said a couple minutes ago, we want to think about as quantity of water, and usually it is a volume over time, gallons per minute. Something very common if you've ever done anything with your house or heard your parents talking about doing stuff. You know, you have flow rate of your sinks, your toilets, and so on and so forth. Gallons per minute is a very common thing, or with wells, they want to make sure you get enough water coming through. This other one, CFS, cubic feet per second, gallons per minute's a little small in a lot of cases. So we move up to something called cubic feet, again, that's volume. Cubic is volume. So per second, and that's a much bigger flow. And there's others. These are just two very common ones. And the connection here is, generally speaking, again, everything else being the same, a stream with more water in it is going to flow faster than a stream with less water in it. Okay? We've actually got a little bit of math to help explain why here in a moment. But if you go back to those stream channel examples, okay, remember I told you we were keeping the volume of water constant in each one. Now if we go back and change that, but keep the channels consistent, like that first one, the smooth, narrow one, all right, the one with more water in it should flow faster than the one with less water in it. And I can't stress enough that these are generalizations. All right, a little bit of math. Some of you won't even need to use numbers, but if you do, we'll show you how to keep it simple. So Q equals VA is our stream discharge formula. You guys, when you went to the stream, you stuck that big blue stick in the water and it moved a propeller and it did all the math for you for getting velocity, okay? You also took width and depth measurements. In theory, the reason why you did that was to calculate the flow rate of the stream. We didn't end up doing that, but you took all the data to do that. Q equals VA. Q is the quantity of the water. That's the discharge. That's what this equation is set up to measure. So what we're saying is that the discharge is a function of, or the quantity of water in a stream is the function of, the velocity of the water and the area of the channel. Just reading the equation as a sentence. And I wish I'd done that a lot earlier in my career. I would have gotten through probably some of my classes a lot easier. Read equations as sentences. So the amount of water that can flow through a stream is a function of two things. How fast that water is flowing and how big the stream channel is. All right. And as I said, we're not Mother Nature. She just does all of this. When I ask you to manipulate this, all right, I realize there's no math requirement coming into this. Not a problem. Just about every single one of you can do the little bit of math that we might do. It's just algebra. If you could do 25 equals 5 times 5, you can do this stuff. All right? So we keep it simple. Mother Nature does not. All right, so we're going to talk about two streams side by side. Why they're side by side, who knows? It's a story I'm telling. So you got two streams side by side. All right, one of them is wide, one of them is big, and the other one is small. All right. Oh, and they're flowing at the same rate. So remember our three variables, right? We had Q, we had V, we had A. So A is the big and the small channel. And the rate is V. Sorry, brain fart for a minute there. So what we're figuring out is Q. All right. Which one's going to have a higher Q? The big channel or the small channel if they're both flowing at the same speed? Which one's going to get more water through? The big one. All right, you all got that. How come? Because there's more room. We also have to give, for example, an unlimited supply of water. That goes without saying. It's always flowing as much as you need. Okay? It's bigger. You could just get more through it. It is that simple. All right? We have another example. So now we've got two streams of the same size. So A is the same, but we've got a fast V and a slow V. Which one's going to have a higher Q? Which one's going to get more water through? The fast one. All right. Why? Because, again, given an unlimited amount of water, you're going to get more water through. If you stand at this one place and count cars on a highway, all right, one lane's going 35, the other one's going 65. Which one's going to get more cars through? The one going 65. Okay? It's the same idea. You're literally standing there next to the stream, counting every little water molecule that goes by. If you have an unlimited amount of water and you got a big stream and a little stream, big stream's going to get more stuff through. That's all the relationship is. And like I said, some of you just know that if you move V or A up or down, the other one has to do the opposite if Q stays the same, or vice versa. I'm never going to give you guys numbers. I'm going to give you words like we just saw. What happens to this if we do that? If you need to do math for you to figure it out, keep it simple. Something you know. 25 equals 5 times 5. Whatever. Something you know is true. Plug it in and replace Q equals VA with something you know is true. So what are we doing here? What happens to your velocity if the area decreases? Okay, so 25 is Q, V is 5, A is 5. That's our setup. I asked you to decrease A. So we're going to keep 25 the same. We're going to make A smaller. I just picked 3. Could have picked 4. That's fine. I just randomly picked 3. So the question is, what happens to V? Okay. Again, without even doing the math, some of you know that it'll increase. But to do the math, you got to divide each side by 3 to isolate V. And when you do that, you get V equals, apparently 8.33. I figured it out with a calculator one day. But V goes up. All right. If you need to use numbers, keep it simple. Same thing, now we're going to vary what happens to velocity as the area increases. Okay, and here it is with math. So we're increasing A this time. We still have our setup of 25 equals 5 times 5. We're going to make that area go up to 7 instead of being 5. 25 stays the same because we have the same amount of water. V decreases. It drops. Okay? So it's math, but don't let it scare you. It actually makes sense for a change. Okay? Simple stuff.
Velocity actually increased more than what it would be yeah, in the last one.
Yeah. Oh, a similar drop in one is bigger and change in the other.
Well,
Interesting.
Almost is.
I went up 2. I think I went down. Well, now you got me wondering.
You went down 2 that one, but the other one you went up 2, but it was a smaller increase.
Yeah. That's funny. I was just having the same argument about the area of a rectangle with one of my children. Brownie pan. All right. You need a 9 by 13 pan. And so I gave an 8 by 12. This is harder math than we used. But 9 by 13 is not the same. 9 times 13 is not the same as 8 times 12. Right? Won't know if you do that. What is 9 times 13?
117.
Oh, stop. Show off. All right, what is 8 times 12? And 96? Yeah, I think so. So you went up 1 inch on one side and down 1 inch on the other side. Why isn't it equal? That's exactly what you're asking here. In my simple brain, it damn well should be equal, but it's totally different square inches. And my one son, my daughter's still only 13. My son, he's always been through all the math. He's trying to explain. He says, "Dad, it's the nature of the rectangle." And I'm like, okay, whatever. It should be the same. We went down 1 and up 1. It equals out. It's not the same. Not the same. So we ended up with, a different thickness then because we messed with the laws of Brownie. You guys got different sinks in the environmental science lab than we do down in geology. In geology, we just got one big basin at the end. You guys got all those silly little ones in the middle. There's a couple big ones, though. So in my lab, everyone comes down at some point, whether they want to wash their hands or fill up a beaker or something. They turn on that spigot, and what happens? Whoosh! It splashes all over the place. You may have done it in high school. Okay. And I'm telling you that that's on purpose. Do they want to soak you? No, that's not their point at all. But think about what's going on here. Think about why it's happening. So that water has been traveling through whatever size pipe it's been traveling through the whole way round through.
And yeah, it's probably been downsizing as it comes through the building, but once it gets into the building, it's probably fairly normal. So it's traveling along in its journey, and then the last 3 inches of its journey, it goes from something the size of a big old fat Sharpie down to something you could barely even fit the eraser or your pencil in. In like 3 inches, it goes through that change. That's A. All right. Q has stayed the same the whole time through. Hit the same amount of water. And then all of a sudden, in the last 3 inches, very, very rapidly, you're changing the area. That shoots the velocity through the roof. The reason is, and it's purposeful here, that nipple, they call it a nipple, that nipple is on there so you could put a pipe onto it, a tube, hosing. And then since you're putting hosing on it, you also need to have some motivation for it to flow. So there's your velocity. So that's so you could run water to somewhere on the table, which we've never done. But apparently at some point in the past, they used to have to do it a lot because every single one of these lab sinks has that on it. But yeah, so that's what's going on there. Much more practical application. You may not live in this situation, but you've driven by or may have a friend or family member that does. You know how some places, instead of a sidewalk, they've got a ditch between the road and the yard, right? And because, I really wish we still did, but because we don't have drawbridges anymore.
Drawbridges. Wait,
All right.
drawbridges are those, what are they again?
Yeah, when you lower up a big plank over a moat or something like that, and the big chains. A what?
Draw a shipping path or something?
Or more so to isolate your castle from warriors, but yeah.
Oh, yeah, I know that.
Oh yeah, no, I know what you're thinking of. Yeah, that's another use of the word. Yeah, but same idea. But no, I'm thinking of the ones like with knights and castles and stuff. And as a homeowner now, I'm kind of glad I don't have to maintenance one of those. But nonetheless, what do we do instead? We've got a big old pipe running there, so then we put our driveway on top of that, right? So think about the ditch before it and think about the ditch after it where the pipe is. So before it, and we've had all this conversation about stream channel size and all that stuff. You've got just a wide, arguably rocky, maybe grassy ditch. The water's flowing through there. All of a sudden, it hits that nice, smooth pipe. Well, that's like a water slide for the water, pardon the pun, but it just, woo, it's super fast, super nice. And you get out on the other side, that velocity has actually kicked up a little bit. And we've actually taken steps to fix this because we noticed it, and even though, again, they knew the math, kind of like me not processing the whole staggered starts for runners, it took us a while to figure this out. On the downslope side of that pipe, it's all eaten away, worn away, because that water comes through a little faster, and it digs out the sediment, and slowly but surely, the downslope side of that ditch gets a little wider. So what do they do to the tubing? It's corrugated. Now, that makes it a little stronger, too, which helps with the driving over it on a daily basis. But also, it slows down the water. So it doesn't wear away on the downslope side. Real life stuff here. All right.
We got some like 15 minutes left.
Yeah, beautiful. Just what I need. Just what I need. So, we've been talking about this the whole time. We're just finally giving you some vocabulary words for it. When we talk about streams and erosion, there's a couple terms they use. One of them is competence, and the other is a term called capacity. We are much more interested in competence in our discussions. Competence is the grain size that stream can move. All right?
Quick question. Does the competence usually mean like being able to do something?
Yes, and that's exactly what it means here.
And
How competent is it? How capable is it of moving? Now, you guys, you didn't have, this is from my geology class, boulder, cobble, pebble, sand, silt, clay. Those are your grain sizes, okay? What are you capable, to borrow his word there, what are you capable of moving on a normal day, any given day? Not during a drought, not during a flood, just a normal day for that stream, all right? And most streams are capable, certainly, of moving silts and clays along, mud, as you think of it. Sand, yeah, it's moving along down there. The water can pretty much move sand. And pebbles, yeah, if it's moving it a good bit. Cobble, think of like a head of lettuce, bowling ball. It's kind of big. Boulders, you know. So no, that's off the end of the spectrum. But on a normal day, what is the stream's capability? What is its competence? Capacity, that's for other folks to worry about. That's total load. Think of it as a big old dump truck. How much sediment can it actually move? It moves 3 tons in a day or 3 tons in a week. And again, we don't typically worry about that so much. Both of these are tied to the stream velocity. How much energy is in a stream? Yeah, question.
How do they determine the actual amount that moves? So would it count if it picked
For
up
competence or capacity? Which one are you asking about?
capacity?
Okay.
If it picked up a rock and then moved it like a few feet and then dropped it, would that be considered that? Or does it have to like move it far enough to where it's...
You know what? I'm sure for the folks that are in charge of this stuff, they might have some measure of ability. As it turns out, we have a word. There's one, sand grains in particular, is quite frequent, common. So they have a word for this hybrid of really trying to move sand. You'll see it in a minute. But yeah, I'm sure the hydrogeologists have some criteria. I'm not familiar with what it is. And more so, knowing them, they're not going to stand there and watch it so much as say, generally speaking, it takes this much, a velocity of this much to move something of this size. And as always, there's 6 other factors, blah, 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 blah. But I'm sure it's something as simple as math these days. But you're just not going to see, I shouldn't say that, you're not going to see a river moving a boulder on a normal day kind of thing. You know, it's just generalized statements you can safely make for the most part. But. So competence and capacity, and as I said, they're really tied to velocity. Yeah, there's the size of the stream, of course. You could have the same conversations. A big stream is capable of moving more sediment than another stream. You can't move a boulder through a stream that isn't wide enough to have a boulder in it. You can get all silly, but we talk mainly about velocity, okay? And then the application of this is, again, in that during periods of heavy flow, high Q, all right, a stream will move bigger and more sediment. Both your competence and your capacity increase, all right, as your amount of water in the stream increases. And they both drop as your velocity drops. So that's the big connection there to make. So with relation to, or with discussion to capacity, we want to talk about a couple ways in which sediment is carried through a stream. And we got 3 of them. We've got dissolved load, we've got suspended load, and we've got bed load. Dissolved, suspended, and bed. Dissolved, suspended, and bed. All right. Dissolved load is well, just that. There's no grain size involved here because the stuff is dissolved in it. And you might not have thought about this, but it is erosion. So we've talked about maybe you might have hard water. You talk about how you might have iron in your water, or you went to somebody's house and they had kind of sulfury water, tasted like egg. That stuff had to be dissolved in some point and somewhere. And from that point to where it's coming out in that faucet, that's transportation. All right, kind of silly, but it is. It was also weathered out up here where it went into solution, so on and so forth. So dissolved load is just that. Something dissolved into the water further upstream, and it's going along for the ride, and it might not get deposited, for a very long time. All right, suspended load, you're much more familiar with. Suspended load, just rained like crazy. You just walked past or drove past your favorite stream, and hey, it's not usually chocolate brown like that. What's going on? Well, and someone will say, oh, it's all muddy right now. All that mud is washed into the creek and da-da-da-da-da-da. Well, that's exactly what is going on. It's silts and clays. Silts and clays are what we call mud when they're wet. And there's that supposedly age-old experiment. I've never seen a teacher do it. I've never done it because who has time to stop on their way to class and grab a cup full of muddy stream water? But they always talk about it like there's these teachers that do this. So if you took a beaker full of one of that muddy stream that one day, you could do this at home. I guess that's where it'd be best done. And then take that beaker and set it on your counter for a couple hours. You could all pretty much guess what's going to happen, right? That sediment is going to settle out. The water's going to be clear. It wasn't actually chocolate brown after all. It was the turbulence that was keeping those fine particles suspended in there, okay? So that's what helps the suspended load stay suspended, the fact that it's moving. They're light enough. They're sort of floating along for the ride there. And again, those are clays and silts. Lastly, we have bed load. Bed load is along the stream bed, the bottom. And it is stuff that is, please ignore the rolling and sliding. We're not going to worry about that. You know stuff is banging around down there. How it moves, we don't really care about right now. All right. That's your heavier stuff. That is sands. That is your gravels, what we would call pebbles, and maybe approaching some cobbles, again, depending on how strong the stream is. But, to what Luke was saying earlier, we've got something called saltation. It's kind of hidden in there. You see the word sand moving by saltation. Saltation is a very specific word and has nothing to do with salt. It's the water trying to carry a sand grain. Picks it up for a little bit and says, I think I can do it. This is too heavy. And it sets it down. And then a minute or two later, it picks it up again, and it makes it look like, if you were standing there watching it, it makes it look like it's bouncing along the stream bed. Follow the bouncing ball kind of thing. Okay? So saltation is sand, a hybrid of suspended load and bed load. It's sand grains bouncing along on the bottom. Now, you got to wonder why they make such a stink, and to the point of creating a vocabulary word for something as silly as this. And I almost think it's to really help illustrate the fact that this is so tied to velocity and also seemingly to sediment size. And also enough for us to say that quite typically, a normal day, you're not going to see sand floating along in the water column. And you could probably agree that you've never seen sand floating down a stream. We've seen sand deposits. We've seen gravel deposits. The bars on the sides of the bends, like we talked about an hour ago. But you don't see that sand floating. So it's usually just rolling along the bottom. But it could happen. Could happen. So this is just sort of a summary slide here. All right, it talks about our three ways for erosion. We've got bed load, suspended load, and dissolved load. Saltation should probably be bumped in another tab, but bed load is pebbles and sand. Suspended load, silts and clays. Dissolved load, calcite, iron, silica, sulfur. I mentioned silica, but and then we have saltation, which is that hybrid, that mixture of suspended and bed load. And again, it refers only to sand.
Yes.
All right, so we're not going to talk about flooding. We're not going to go through the flooding slides, I should say. So if you did print out these PowerPoints, we just put some X's through these because we're not going to get into the nitty-gritty here. But I do just want to talk for a moment because, again, real-world application, this is something that unfortunately you may have to, if you haven't already, deal with in life. And, you could assume that that guy didn't park his trailer on the stream last night, and those cars...
Wait, where is this?
I don't know. And those cars weren't parked in the river or upside down for that matter. We've all seen the horrific footage, perhaps as a flood is going on, and something that definitely should not be carried is getting carried downstream. All right, and they talk about the power of the flood, and well, we know now we're talking about that system energy. That's that quantity of water. That's that velocity of water. And you may have, again, depends where you grew up. I didn't grow up, but I lived 20 years about a block from Sequoia Creek, and we kept an eye on streaming quite a bit. And you'd see when she's starting to get chocolate brown and flowing a lot faster than normal when I would let my kids go down and play. And then you guys are not going to the stream today, okay? But you don't call that a flood. Even when it's really high and really fast, it's still not a flood, right? Until it comes up and over. Well, we did tell you about when the streams come up and over. We told you that they slow down, because otherwise we wouldn't get those levees. We wouldn't get the floodplains. Well, the point is that at some point, they sort of rechannelize, whether they hit a curb or, God forbid, whatever, row house, who knows what. They rechannelize, and that queue keeps coming. That's where that constant flow is the bad part. And once that queue keeps going up and you've rechannelized, you've got a new A, then that velocity can go right back up. And that's when stuff that's sitting in your driveway or whatever starts going down the stream. You've seen the deposits left behind, and I'm not talking about the sediment, but when you're walking through the woods and you see a whole bunch of twigs and reeds and grasses and whatnot plastered up against a tree. You may or may not have known that was put there by the last time the river flowed through there. All right. So we see evidence of this all around us. Not to this extreme usually, thank goodness. But all right, so jump back to this last slide since we have a minute or two left. All right, and so the rapids. We told you that rocks slow stuff down. Surface area, friction, it should make things slower, but we've been through there on our canoes or our kayaks, and we know that it is not that way, at least seemingly. Now with all the stuff that you know, Q equals VA and whatnot, anyone want to hazard a guess as to why rapids are rapid? Well, there's no one answer, as it turns out. There's a lot of stuff going on. A lot of these rocks that you're paddling around are too big to be moved, quite obviously. All right. And one of the things that happens is this stream that was a single channel is now potentially several smaller channels. So you got to recalculate all of your Q equals VA stuff. And obviously, at least based on observation, in many cases, that V is getting jacked up, okay? Probably because A has gone down. Additionally, though, and probably more the factor, is turbulence isn't quite the right word I want, but the water flowing around those rocks. That's the fun part, right? When you're in there, and I think it's crazy, don't get me wrong. My family does do this, but I like the nice, smooth streams. But those eddies, when you're going around in the currents, that, even if you're not going faster, you've got that varying movement, and it feels, it's fun, okay? So that's what's going on. Yes, what we said earlier is still true, all right, about friction should slow things down, but there's enough other factors. Again, Mother Nature doesn't need to do simple math. There's enough other stuff going on that it overcompensates for it, and it's good to go. All right.